So, welcome to what will hopefully be a semi-faithful recreation of my SIGGRAPH talk, or at least as faithful as it can be without a giant Canadian-sized bottle of Red Bull and the fear of speaking in front of 500 people. Okay, so hope you guys enjoy it. For those of you who didn't get a chance to see it, and for those of you seeing it twice, yeah, go watch something else. Okay, so I'm going to be talking about PixelJunk Shooter 2, reviewing some of the fluid dynamics stuff we did, some of the particle stuff, and then go on to talk about a little bit of the SPU lighting. I'm Jamin Kessler, Q Games Technology Team, and Okonomionda on Twitter, so feel free to follow me if you feel so inclined. Okay, so I'm going to go ahead and jump right into fluid dynamics. It's going to be a roughly 15 to 20 minute talk, so go grab a coffee or some Red Bull and let's get started. Okay, so for those of you who have never actually played Shooter 2, I'm not going to make fun of you or ridicule you or anything. I'm just going to kindly introduce you to the game so you know what I'm talking about. It's an environmental puzzle-based shooter. And what do I mean by that? It's not a term you throw around very often. So we have puzzles that are based on the interactions between various solids, gases, liquids, and magnetic fluids, lasers, ice, all this stuff. So some of the reactions that we try to simulate is, for example, water cools to form magma, water cools magma to form rock, magma melts ice and rock, magma ignites gas, all this. Well, you can read the slide for yourself. You don't need me to narrate it. And my personal favorite, when you mix magnetics and water, it forms a poison gas. I don't know why. So everything is organically arising from our simulation, meaning nothing is scripted, nothing is kind of preset up. Every time you play, you'll get different reactions because everything's just a little bit different each time. So here is a video for those of you who have never seen it before of basically something I want to demonstrate. So it's this type of reaction that you see in the game. So I'm here in the lava. I have my inverter suit, so don't worry, I'm not going to die. So I'm going to go ahead and shoot the lava into the gas. The lava is going to ignite the gas. The gas is going to melt the ice that you see on the side, which is going to turn into water. Then the water is going to hit the magma and cool the magma into rock, and then eventually the magma will melt the rock back into magma. So it's, you know, this kind of stuff that the game is basically based around. Okay, so it's a particle simulation for the fluid, and we went with Verlet integration. Some of the good points: it's fourth order accurate, it's way more stabler than Euler. Damn it, I knew I was going to say that. Euler. By the way, I'm trying to be more Khan Academy-like in my videos, and I don't mean, more intuitive and easy to understand. I mean more, I just keep talking even after I screw up. So yeah, it's greater stability than Euler, and in certain cases, if you don't screw it up, it's time reversible. Some of the bad points is it has a bad handling of variable time steps, which is, there's a time-corrected version to help with that, and you need 2 steps to start out, so the initial conditions are fairly important. So if you look at the diagram on the right, we actually need to get the position at t plus delta t. You need it at a position at t, and then you also need some stuff at t minus delta t. So those are the initial 2 steps to get the next step. Okay, so one problem that we ran into is that basically in this model, flow is supposed to be non-compressible, but because gravity pulls down on the particles, things start to get a little compressy down at the bottom. You'll see in the image on the right-hand side. So the trick was to give the particles an adjustable radius bias and a repulsive force between them. So the radius, the size of the expanded radius basically depends on how many particles are all up in your personal space and how close they are to you. And we basically take the max ingression of all the surrounding particles. We have 2 different rates of lerping, and contraction is about 4 times faster than expansion. Okay, so there's some differences in particle types too. They're not all of the same processing, I guess. So particles have different masses depending on what they are. Some have rigid bodies, some don't. And then you also have different properties based on combinations of particles. So when 2 different particles meet each other, for example, magma and water, they repel each other with different forces, which I seem to have listed twice on the slide. They have different chemical reactions simulated between them, and they propagate heat differently. So you think about heat propagation, it's basically what you saw before, where water and magma come together, and the magma gets hardened, and then magma eventually melts rock back into magma. So each particle carries some thermal data with it, and when the particles collide, heat's propagated. And just like in real life, we go warmer to cooler. Same algorithm we use in the particle update for the interparticle repulsive force, and they all have different thermal transfer values. So here you see at the bottom heat going to cool, and then they reach equilibrium, and then there you go. Okay, so there's a couple different stages to the fluid particles. We start off doing some collision detection and repulsive force calculation. Now keep in mind that this is a grid-based simulation. We divide the screen into 44 by 28 cells just to basically give us a nice unit of work to divide up among the SPUs so they can grab multiple cells. So for each cell, we're going to do collision detection, repulsive force calculation. Okay, now a particle can actually be in 4 cells at once if it occurs on the corner of 4 cells. So what we need to do is we need to process this particle in the next stage in all 4 cells. So we basically take, or we process it in all 4 cells. We want to take those forces that we calculated in all 4 cells, and we want to unify them. So that's force unification across grid cells. Next is the Verlet update. This is our heaviest job. It does a lot of stuff, not just Verlet update. It does turbulence effects, like when you get a sudden change in fluid direction. Next is particle deletion, which is our only thing which runs on one SPU. And then finally, grid calculation for the next frame. Now I'm going to show you the Spurs chain in depth later on. So just remember, once I introduce the particle processing that we're doing for the lighting, or the processing we're doing for the lighting, then I'll show you everything together. But for now, I'm just going to give you a text description of what's going on with the fluids. Okay, so we have 2 methods of collision that I wanted to mention that I think are not necessarily brand new, but just something cool that worked for our game. So characters, missiles, and other games and other objects in the game, we surround them with these particles. If you look at the picture in the bottom of the screen, you'll see the ship itself and the power-up item and the survivor in a bubble are all surrounded by these interactor particles. And it uses the existing particle system, and it gives us a way to really, really simply detect and track collisions with anything. Now, what you're seeing here is these are all items that you might want to grab with your little ship grabby hand that comes out and grabs things. So that's one way that we can do that. Oh, throat's getting dry already. Okay, so this is just showing you what the interactor particles look like in action. You'll see the survivors at the top, the diamonds at the top right, the little pulley lever thing you have to grab. I don't know what the technical term for it is, are all surrounded by these interactor particles. Okay, so the next method of collision, which seems to be all the rage today that all the kids in the ray marching world are talking about, even though it's not new, is collision via distance field. So I'm not going to go into the description of distance field, since that's something you can easily just look up and most people already know it. We're using a signed distance field, 256 by 256, running on a single SPU, because the parallel versions were kind of annoying to work with, and a lot of them were for made-up machines that don't even really exist, but they all had some problems. But on a single SPU, we're looking at 0.5 milliseconds for 256 by 256, so there was really kind of no need to take it any further, as much as it hurts me to say that. We have 2 different distance fields. There's a static one for things that can't change, and then there's a dynamic distance field recalculated every frame for destructibles, like walls that you can blow up, and fluids when they harden into rock. There's things that change in the world, and we basically go ahead and merge them into a final distance field. And the cool benefit of this, my personal favorite thing about it, is that it becomes one single lookup to get not only the distance to the closest object of anything on the screen, closest wall, but you can also get the direction. And we use this for the SPU lighting, because it would be very multi-nai to have it and only use it for one thing and not really kind of find other uses for it. Okay, so this is just the same example that I showed you before, except this time with some debug information shown. So you want to basically watch the texture in the upper left corner. That's going to show you our distance field. You can already see where the walls are right now. So as I shoot lava up, you'll see walls disappear as they blow up, and then as the water hardens the lava into rock, you'll see new walls appear. It's upside down, so don't get confused. And this is another debug tool we have that shows you the output from the distance field. So it's giving you the distance and the direction to the closest wall. Notice that because it's a signed distance field, when it gets inside the rock, it doesn't go to 0, it points to the nearest edge. So you're looking for the closest border between a wall and a non-wall. Okay, let's get into some fluid rendering stuff, since this was at a graphics con that I gave this presentation. Okay, so it's cool to have particles, but particles a liquid do not make. You have to render them as a smooth flowing fluid. For example, what you would do with marching squares, which may or may not be patented. I'm not gonna tell you my opinion of software patents or patents in general, but you can get that on Twitter. But the point is that we ended up trying to find something else that was a little bit, I guess, computationally less intensive. So what we ended up doing, very simply, was rendering particles to a low-res off-screen buffer with a luminance texture. Blur that, scale it up with bilinear, and just use that brightness to color the liquid. So you can see the 3 stages at the bottom of the screen, and then on the right being the final tinting of the water. And speaking of tinting, another thing we wanted to do is we wanted to have a little crust on the edge of the water, a little, that was my wife laughing about something. She must be watching something funny on her laptop. I don't know what it is. But, so we use a smooth step function when we render water to the off-screen buffer, and we just basically use 2 different thresholds for the surface and for the water, and that gives us our tint. Oh, by the way, you could see the bubbles in this, which was some of the turbulence effects that I was talking about before when I said, we do some other things in our update job. Cool, cohesiveness. This was a big problem. So it's the opposite of the compression problem that we had. So instead of particles being forced together in a free-falling liquid, they can kind of drift apart, which is what you're seeing on the left. And we have nothing keeping them together. So to get from the image on the left to the image on the right, we needed something to fill in the holes a little bit. So what we ended up doing was just not fully clearing the off-screen buffer that we render into, and the image lag kind of gives you this cohesiveness effect to it, although it does sort of break down in one case, which I'll show you now. Okay, so here is the particle system rendered without a smooth flowing liquid. So you could just see the particles. We're not rendering any surfaces here, just straight particles. And this is what the lava looks like when it falls. Okay, now here we have with the cohesiveness hack turned on, and then here's the thing with the magnetics. Because you have this lateral force that's not usually there, kind of pulling off to the side, holes tend to open up in the fluid, but at the same time, because it's this slick magnetic kind of thing, it really looks cool. It doesn't look bad in any way. It's a really cool effect, but just to let you know, the magnetic thing does sort of break this cohesiveness trick that we're doing. Okay, one thing I should say though is that for those of you who have played Shooter 2, you'll notice that the stuff that I used in that last video is actually not from the game, it's from SideScroller, which is pretty much done in the same engine. And the reason I use SideScroller is because, well, for the main reason that particles and the fluid are rendered as actual particles. We're not rendering them as a smooth flowing surface. So if you look at the bottom here, you have some magnetic fluid that's rendered as a bunch of triangles. And it was just a very, very good way to basically show you, because it was very hard for me to figure out in Shooter 2 how to turn off the surface rendering. It just wasn't something I can do in the short amount of time I had to make the video. So it was just easier to use some footage from SideScroller. It's in engine, so don't worry, nothing going on. Okay, so we want to depict movement among the flowing liquids. So we do this basically simply enough where when you generate a particle, it gets a random RG value. And whenever that RG value is close enough to 0.5, 0.5, we give it a different coloring. So what you're looking at is basically on the right, that's how we get the pattern in the lava. The lava is all one color, and then where that RG value is just right there in the center, we go ahead and we give it a different color, which creates a pattern and gives the illusion of flow as it kind of moves along.